Hi everyone, welcome to our learning video sessions on Microsoft Excel for chemical engineers. This is our 13th video lesson and the last video lesson on the series of Microsoft Excel for chemical engineers. This video lesson teaches how to use Microsoft Excel software for the McCabe Thiele method to determine the number of stages in a distillation column. We hope that you learned the McCabe Thiele method when you learned the distillation theory in the unit operations class. So we are not going to teach you the theory behind the McCabe Thiele method in this video lesson. If you have tried to draw the McCabe Thiele diagram manually, you might already know that it's little difficult and the accuracy could be different from person to person. So when you use Microsoft Excel software to draw the McCabe Thiele diagram and for the associated calculations, a better accuracy of the solution can be obtained. The focus of this video lesson is to show you an additional method to improve the accuracy of your calculations. So let's take an example problem and see how to use Microsoft Excel software for the McCabe Thiele method. Acetone is to be recovered from an aqueous waste stream by continuous distillation. The feed will contain 10 weight % acetone. Acetone of at least 98% purity is wanted. And the aqueous effluent must not contain more than 50 ppm acetone. The feed will be at 20 degrees Celsius. Estimate the number of ideal stages required. Column operates at 1 atm pressure. Let's start the example solution in Microsoft Excel while reviewing the procedure for constructing the McCabe Thiele diagram step by step. You can see that we can prepare an Excel spreadsheet to perform necessary calculations in order to plot the McCabe Thiele diagram. So we have entered the given data for the feed, top and bottom mass fractions. First we have to convert the mass fractions into mole fractions. We can assume that the aqueous solution contains acetone and water only. So taking the molecular weight of acetone as 58 and water as 18, we can calculate the acetone mole fractions in the feed stream, that is XF, top stream, that is XD, and bottom stream, that is XB. The first step of plotting the McCabe Thiele diagram is plotting the vapor-liquid equilibrium curve at the column operating pressure. You can use the equation in terms of the relative volatility of the more volatile component with respect to the less volatile component in order to calculate the equilibrium vapor-liquid compositions. In this example, let's use the equilibrium data for the acetone-water system available in the literature. It's better to draw the diagonal of the plot, that is the x equal to y line, in the diagram before plotting the vapor-liquid equilibrium curve. So we can take the 2 points such as 0, 0 and 1, 1 to create the diagonal. So let's insert a scatter diagram. We learned how to plot scatter diagrams in Microsoft Excel in our fourth video lesson. Let's make some formatting for the better looking of the graph. Now, right-click and select data for the diagonal first. Let's name the series as diagonal and select X and Y axis values. In the same way, insert the graph for the vapor liquid equilibrium data. Let's name the series name as equilibrium and select X and Y axis values accordingly. Let's apply some formatting for better looking of the graph lines. The second step is the Q-line drawing. Q-line means the line on which the intersection of the top and bottom operating lines occurs. The point of intersection of the two operating lines depends on the phase condition of the feed. To generate the Q-line, we should calculate the value of the ratio Q, which is the heat to vaporize 1 mole of feed divided by the molar latent heat of the feed. The slope of the Q-line can be found from Q divided by Q minus 1 intersecting the diagonal at XF, that is the feed composition. In this example, bubble point of feed is 83 degrees Celsius. From the latent heats and the mean specific heats of water and acetone, we can find the latent heat of feed is 40,933 joule per mole and the specific heat of feed is 77 joule per mole per degree Celsius. Heat to vaporize 1 mole of feed is 45,786. So we can calculate the Q value as 1.12 and the slope of the Q line is 9.43. Now let's insert the findings for the Q line into the Microsoft Excel spreadsheet. The Q line intersects the diagonal at the feed composition XF. So we can have 2 points of the Q line. One is the feed composition and the other one from the slope of the line. To draw the Q line, right-click on the plot area and select data for a new graph. Let's enter the series name as Q line and select the X and Y values of the 2 points. Here we obtained the Q line on the same diagram. The third step is the drawing of 2 operating lines for the top and bottom streams. The top operating line intersects the diagonal at XD. To draw the top operating line, we need at least another point. So we can select a value for the minimum reflux ratio and determine another point. The extended top operating line cuts the y-axis at xd divided by 1 plus reflux ratio. So let's assume the minimum reflux ratio as 0.6. Then we can find the other point at x is equal to 0, y is equal to 0.94 divided by 1 plus 0.6. Now we have the other point, so that we can draw the top operating line. The condition of minimum reflux occurs where the top operating line just touches the equilibrium curve. We can see that the top operating line that we have drawn is slightly away from the intersection point of the Q line and the equilibrium curve. One advantage of using Microsoft Excel is that we can change this assumed minimum reflux ratio value to obtain the correct top operating line. So we can adjust the R minimum value. So we can obtain that the intersection occurs at R minimum is equal to 0.45. For this problem, the flows above the feed point will be small. So a high reflux ratio can be justified to make the condenser duty to be small. So let's take reflux ratio is equal to 3 times minimum reflux ratio, that is 1.35. Now the point at which the top operating line cuts the y-axis changes with the actual reflux ratio value. So here we obtained the actual top operating line. If we use the manual method, this step would be difficult and not so accurate like we did in Microsoft Excel. Let's continue the drawing of the bottom operating line. We know that the bottom operating line intersects the diagonal at xb. So we have one point. The other point is the point of intersection of the top operating line and the Q line. In order to obtain this intersection point, let's find the equations of the Q line and the top operating line. For the Q line, we know the slope is 9.43. The B1 value can be found by substituting one of the known points, let's say 0.033, 0.033, that is the feed composition. Then, for the top operating line, the slope can be found using the known points. Substitute one of the point to obtain the B2 value. Now here we have the equations of the two lines. The intersection of these two lines occurs when the two equations are equal. Applying this relation, we can find the x value for the intersection point of the Q line and the top operating line. The y value of the intersection point can also be obtained by substituting this x value to one of the equations of the Q line or the top operating line. So now we have the other point for the bottom operating line. So we can draw the bottom operating line on the same diagram. You can see that we have successfully and accurately drawn the McCabe Thiele diagram using Microsoft Excel software. The beauty of doing this in Excel software is we can use this spreadsheet like a program for the McCabe Thiele method. If we change the values such as the R minimum or XF, XD, XB values, we can quickly generate the diagrams. But when we do this manually, it takes a long time to redraw the diagram at different parameter values. The last step of the McCabe Thiele method is the stepping of the number of stages by starting at XD and XB. Stepping off means we have to draw horizontal and vertical lines by intersecting the equilibrium line from the operating lines. We can use the straight lines in the shapes in Excel software, and we can draw the horizontal and vertical stepping off lines by intersecting the equilibrium curve, as you can see. Let's start the stepping off by starting at XD. Let's draw the lines one by one. You can see the stepping off in the top section. If we draw this manually, drawing the stepping off lines above y is equal to 0.8 must be done in a larger scale diagram. So manual method has to draw many diagrams in larger scale, and the possibility of mistakes and errors is high. We can see that total 7 stages are required above the feed. For the bottom line stepping off, manual method is further difficult for this problem. But we can zoom in the diagram in Microsoft Excel and draw the lines accurately. We can see that total 9 stages are required below the feed. So the final answer for the total stages required is 7 plus 9 is equal to 16. As the final remarks, please note that when you use McCabe Thiele method to determine the number of stages, the feed stage should be located on the stage closest to the intersection of the two operating lines. The McCabe Thiele method is one of the most important concepts in chemical engineering and is an invaluable tool for the solution of distillation problems. In the theory of this method, there is an assumption of constant molar overflow. But this assumption is not limiting, since only in very few systems the molar heats of vaporizations differ by more than 10%. However, this method has some limitations. The McCabe Thiele method should not be employed when the relative volatility is less than 1.3 or greater than 5. When the reflux ratio is less than 1.1 times of the minimum reflux ratio, or when more than 25 theoretical trays are required. As a summary, in this video lesson, we learned how to use Microsoft Excel software to draw the McCabe Thiele diagram. Like this, we can use the tools in Microsoft Excel software in order to make our chemical engineering calculations, graph generations, and process designs easier and more accurate. We hope that this video lesson series will help you to improve your calculation and soft skills prior to learn the process simulation using simulators like Aspen Plus and Aspen HiSys, or process modeling tools like MATLAB software. So that's the end of our video lesson series on Microsoft Excel for chemical engineers. Let's meet again with another video lesson series like this. Have a nice day and goodbye.